Zaschlé nečistoty?
So what?
Kapse Somat Excellence 5 v 1. Naše číslo 1 proti zaschlým nečistotám.
Back at the start of the 20th century, mathematicians were fascinated by the question, just how much maths can we do, not by using our gut feelings or intuitions, but just by following rules very, very carefully, by following an algorithm. In order to make that notion precise, we would have to set out just what do we mean by a program or algorithm. And this is where Alan Turing came in with his notion of a Turing machine. Turing was working on a problem in formal logic, and as part of his proof, he had to come up with a notion of any possible algorithm or any possible machine. He had to come up with a very general way of capturing how algorithms or programs or machines would work. This is where his notion of a Turing machine comes in. The way Turing described these machines goes like this. You have a way of writing down information in a coded form. His way was to think of a tape, which is as long as it needs to be. It's divided up into squares, and on each of these squares there's either a 1 or a 0, or we can have some spaces. Now what our machine does is it looks at the tape one square at a time. So you could imagine it as a little box running above the tape, maybe on little wheels, looking one square at a time. And that information codes up a question or a problem that we want solved. What the Turing machine does is really simple. At any moment in time, it's in a particular state and it's looking at one square on the tape. And it has a logbook, a program book, and that tells it, if for instance you're in state number 23 and you're looking at a 0, then rub out the 0, change it to a 1, move one square to the right, and move into state number 359, for instance. Or if you're in state number 359 and you're looking at a 1, leave that 1 as it is, move one square to the left, and move into state number 20. Really simple instructions. What the machine does is it starts off, move one square to the left, and leave that 1 as it is, move one square to the left, leave that 1 as it is, and that information codes up a question or a problem that we want solved. What the Turing machine does is really simple. At any moment in time, it's in a particular state and it's looking at one square on the tape. And it has a logbook, a program book, and that tells it, if for instance you're in state number 23 and you're looking at a 0, then rub out the 0, change it to a 1, move one square to the right, and move into state number 359, for instance. Or if you're in state number 359 and you're looking at a 1, leave that 1 as it is, move one square to the left, and move into state number 20. Really simple instructions. What the machine does is it starts off with a certain pattern of 1s and 0s. It follows these rules one square at a time, transforming that string of 1 and 0s into a different string of 1s and 0s. And eventually, hopefully, the machine moves into a halting state. It's finished, it's done. And what's left on the tape is the answer to our problem, coded up as 1s and 0s. The answer to, and what's left on the, hopefully, the machine moves into a halting state. It's finished, it's done. Pattern. Move one square to the left and move into state number 20. Really simple instructions. What the machine does is it starts off with a certain pattern of 1s and 0s. It follows these rules one square at a time, transforming that string of 1 and 0s into a different string of 1s and 0s. And eventually, hopefully, the machine moves into a halting state. It's finished, it's done. And what's left on the tape is the answer to our problem, coded up as ones and zeros. That is such a simple process, but it turns out it's the essence of computation. Whatever any computer can do, it could in theory be done by that system looking at ones and zeros on a tape. So that's why we say that Turing, in coming up with this idea of Turing machines, in effect came up with a blueprint for modern digital computers. Those computers manipulate strings of ones and zeros to solve problems. This really simple idea that we find in Turing machines is actually so powerful that all modern computers basically do what Turing machines do. And we use this idea to evaluate the strength of modern computer programs. And that is the top of the hierarchy of program strength. So the strongest program that we can get does exactly what a Turing machine can do. We've never come up with a way of computing things that could do more than a Turing machine. So recently, there's been a challenge to the idea that anything a computer can do, a Turing machine can do. And the challenge comes from quantum computers, which almost seem like they can do things magically. My take on this is that a quantum computer can't do more than a Turing machine, but it can do things more efficiently. For instance, if you asked a classical computer to find you a phone number in the phone directory, you have to look through every single entry. It takes a long time. But a quantum computer can do that more efficiently. Don't ask me how.
Look what happens. If I've read a 0, which I have there, what do I then do? The answer is I overwrite it with a 1.
Call that machine H for the halting problem. If you give me that machine, I can transform it into a different machine, like this.
Of early computer engineers, such as Alan Turing, was whether certain mathematical tasks A major concern of early computer engineers, such as Alan Turing, was whether certain mathematical tasks were computable. To answer this question, a major concern of early computer engineers, such as Alan Turing, was whether certain mathematical tasks were computable. To answer this question, Turing created the Turing machine. What else would you call it? This hypothetical machine uses an infinitely long strip of tape composed of a series of cells with symbols written on them to store the inputs and outputs of computations. It also has a head that moves to the left or right that can read symbols from the cells, write symbols to the cells, and make decisions about what to do based on the contents of the cell and its current state. The state machine is essentially the program that tells the machine what tasks to perform. Every Turing machine must have a start or initial state. Based on the machine's state and the contents of the current cell of the strip, the machine will determine its next state, as indicated by the arrow called a state transition. The machine will also change the value in the current cell and may move the head to the left or right, or keep it in the same place. So, in the initial state, we see that the current cell has value 1. Our state diagram tells us that we will transition to state Q1, change the value of the current cell to a 0, and then move the head to the left 1 cell. Now we are in state Q1, and our current cell has value 0. Our state diagram tells us to transition to state Q2, change the current cell to 1, and keep the head in the same place. Now we're in state Q2, and our current cell has value 1. Our state diagram tells us to transition back to our initial state, change the current cell value to 1, which it already is, and move the head to the right. Finally, since our state is the initial state, and our current cell's value is 0, we transition to the halting state. Change the value in the cell to 0, and keep the head in the same place. The halt state is another critical state that every Turing machine needs. Without the halting state, the machine will keep looping forever and never complete its programmed task. Let's take a step back and look at the Turing machine at a more abstract level. Suppose you have a tape with two values a and b stored on it. We could build a Turing machine that would perform the addition operation on a and b and store the summation back onto the tape. We would simply need to create a state machine that would control the Turing machine appropriately. We could represent this type of system with the black box notation, in which we show our inputs entering a black box and our output leaving it. We could then theoretically represent a machine to perform any legal computation, such as multiplication. More generally, we say that each Turing machine has inputs, outputs, and a program P that describes its behavior. The problem with these types of Turing machines is that we need to create a new Turing machine for every operation we want to perform. As you will learn later, creating hardware is much more expensive than writing software. So creating a new Turing machine for every operation is intolerable. So, Turing invented the Universal Turing Machine. This machine had a basic state machine that could be programmed by a machine description P so that to the external user, the Universal Turing Machine would behave exactly like a regular Turing machine that was programmed to do P. Perhaps more importantly, we could feed in a series of machine descriptions to the Universal Turing Machine to perform a series of operations on the data stored on a strip. For example, we could tell the Universal Turing Machine to first perform an addition on B and C, and then multiply that summation with A. As you will learn later, the ability to write small components or functions and join them together will make your life so much easier as a programmer or hardware designer.
S čím jsme pomohli Monice Bagarové?
Já musím říct celkově, že mě překvapilo, jak to bylo velmi rychle. Přijde tým lidí, kteří to všechno vytvoří.
Hi everyone, Jade here. Today's video is an origin story about the entire field of computer science. Now, when I say computer science, I mean literally everything to do with computers. Laptops, desktops, smartphones, iPods, GPSs, quantum computers, literally every physical manifestation of a computer you can think of. But I also mean the theoretical side too, so the study of algorithms, computability and complexity theory, all the kinds of things that a theoretical computer scientist would study. Now, the reason I want to tell this story is because it's incredible. So not only was computer science accidentally created, but it was created from trying to answer a very abstract question about the foundations of mathematics. This story highlights an incredible turn of events, a brilliant thinker, and the interconnectedness of two fields. The story starts with an extraordinary man named David Hilbert. He lived at a very exciting time in the history of mathematics. See, back in the 1900s, it had come to light that no one was really sure what they were studying when they were studying mathematics. When we study biology, we're studying living things that exist in the real world. When we study physics, we're studying real-world phenomena which we can verify via experiment. But math? Was it the study of real-world objects or abstract entities? Did it exist in our minds or in some other realm of existence? The ancient Greek philosopher Plato thought that mathematical objects, shapes, numbers, and the relationships between them belonged to their own ideal world separate from ours. He called it the world of forms. But Hilbert wasn't a fan. He was a modern-day man, and the Platonist view was too mystical and airy-fairy for his liking. An idealized world of forms? Please. Hilbert was interested in down-to-earth matters, what could and couldn't be proven. Another prevailing view, put forward by the German philosopher Immanuel Kant, was that math was a mental construct based on our intuitions. But Hilbert had a problem with this too. After all, intuitions could often lead us astray. The fact that the word paradox exists in the English language is evidence of that.
I've been exposed to such a rich tapestry of cultures.
It's so cool, like we enjoyed it so much the moment we stepped in here.
These differing viewpoints greatly irritated Hilbert. It's not uncommon to have multiple viewpoints in other disciplines. Literature, for example, is praised for being able to have multiple interpretations of the same thing. Even physical laws are revised and changed over time. But math? Oh no, this just wouldn't do. Math was regarded as different from the other disciplines, the epitome of certainty. The fact that 2 + 2 = 4 would never be revised and changed. And it just wasn't good enough that different mathematicians had different interpretations about what it meant. Aside from the prestige of math being called into question, these differing opinions had practical problems too. Those who agreed with Kant's intuitionism didn't believe that the idea of infinity fit within mathematics. Those who thought that logic was the foundation of math ran into logical paradoxes and inconsistencies that limited what they could and couldn't do in comparison with the other schools of thought. You couldn't have different mathematicians playing by different rules. This was just unacceptable, and Hilbert was going to do something about it. He proposed a crazily ambitious program to axiomatize all of mathematics. This sentence requires some explaining. See, Hilbert thought that if we treat math as nothing more than a formal system, there could be no more disagreements about what was and wasn't allowed. So what is a formal system? Well, it's an alphabet or a set of meaningless symbols which can be manipulated according to a fixed set of rules. Chess is a formal system. The alphabet are the pieces which are manipulated according to a fixed set of rules. It's important to know alphabet according. Well, it's an alphabet or a set of meaningless symbols which can be manipulated according to a fixed set of rules. Chess is a formal system. The alphabet are the pieces which are manipulated according to a fixed set of rules. It's important to note that the pieces and the rules don't have any meaning outside of the game. Hilbert thought that this was how we should view mathematics. Something similar had been done by Euclid on a much smaller scale some 2,000 years earlier. By putting forward 5 self-evident axioms and the rules of how to build upon them, the whole system of Euclidean geometry was born. Equipped with these axioms, we don't need to know whether a triangle lives in the world of forms or in our heads to know that its angles always add to 180 degrees. So in this way, Euclidean geometry can be seen as a formal system. Hilbert wanted to do something similar, to find the foundational axioms for a formal systems for which all of mathematics could be built upon. This would eliminate for a formal systems for Hilbert wanted to do something similar, to find the foundational axioms for a formal systems for which all of mathematics could be built upon. This would eliminate any disagreements about what was and wasn't allowed. This was a monumental task, and to start, Hilbert thought about the three main things you would want in a foundational system of mathematics: consistency, completeness, and decidability. Consistency means that no contradictions can be proven within the system. For example, you can't prove that 2 plus 2 equals 4 and that 2 plus 2 doesn't equal 4. Inconsistencies would render the entire system useless. Completeness means that a proof was required that all true mathematical statements which existed in the system could be proven within the system. And finally, decidability. This was the idea that there should exist an effective procedure for deciding the truth or falsity of any mathematical statement. For example, if given the statement P plus Q equals Z, there should be some effective procedure for deciding whether this statement is true within the system. This is where our hero of the story comes along, Alan Turing. You may know him from such films as The Imitation Game or the biggest award in computer science called the Turing Award. At the young as The Imitation Game or the Alan Turing. You may know him from such films as The Imitation Game or the biggest award in computer science called the Turing Award. At the young age of 22, Turing got intensely interested in this last question, decidability. Did there exist an effective procedure for deciding the truth or falsity of any mathematical statement? But Turing saw a slight problem with the question. What exactly was an effective procedure? Today, an effective procedure is considered to be an algorithm, some step-by-step set of instructions that you can follow without using any real thought or intuition. But this was back in the 30s, and the idea of an algorithm was still vague and ill-defined. We're used to the concept now because they're fundamental to how computers work, but computers didn't exist back then, or at least not as we know them today. The word computer referred to people, usually women, who were given a list of instructions and carried out tedious computations by hand. This job required little thought and definitely no mathematical intuition. Throughout his life, Turing was fascinated with the relationship between humans and machines. He's famous for coming up with the idea of the Turing test, a test for determining whether a machine is capable of thinking like a human. This was no exception, as the term effective procedure was too vague to do anything rigorous with. He decided to define it himself. He based his definition on a human computer. He decided that anything a human computer could do by mindlessly following a list of instructions, using no genius or insight whatsoever, was an effective procedure. He thought about the basic components of what a human computer does when they're computing. 1. They read instructions. 2. They read and write symbols on a piece of paper according to the instructions. 3. They occasionally erase symbols and replace them with new symbols. And 4. When they're finished with the computation, they stop. That was about it. And here, finished with the occasionally erase symbols on a piece of paper. 1. He thought about the basic components of what a human computer does when they're computing. 1. They read instructions. 2. They read and write symbols on a piece of paper according to the instructions. 3. They occasionally erase symbols and replace them with new symbols. And 4. When they're finished with the computation, they stop. That was about it. And here is where the truly revolutionary part comes in that would transform the world for years to come. Turing recognized that every step of what a human computer did could be replicated by a very simple theoretical machine. In place of the human could be a scanning head, which could read one symbol at a time, erase one symbol at a time, and write one symbol at a time. The piece of paper could be replaced by an infinitely long piece of tape, which contained one symbol per square. But
you sent in a proposal, but your manager has so many questions. Uh-oh. Let's try again with Grammarly. First,
But how does the machine know what to do? When a human reads a set of instructions, something is going on in their mind which tells them what to do next. Turing thought of these as states of mind. And so similarly for his machines, devised the idea of internal states, which tell the machine what to do. This idea is best understood using visual diagrams and an example. Say we want the machine to perform the very simple task of recognizing when there are an even number of zeros and ones in the tape. This is easy for a human who has mastered the art of counting, but it's not so straightforward for a machine. A simple way for our machine to tackle this problem is to pair a 0 with a 1 and then cross off the pair with an machine to tackle this problem, but it's not so straightforward for a machine. A simple way for our machine to tackle this problem is to pair a 0 with a 1 and then cross off the pair with an X. It keeps doing this until it can't anymore. If it crosses off all the symbols in the tape, we'll know there was an even amount. If it doesn't, we'll know that there wasn't. Now, how do we program our machine to carry out this task? Well, we build it with an internal state table that looks like this. I know this looks complicated, but it's not too bad. Let's read it together. Take this tape with these symbols. We want the machine to tell us whether there is an even number of ones and zeros. The machine starts in the start state. The start state tells the machine, if I find a 0, I will replace it with an X, move to the right and into state B. If I find a 1, I will replace it with an X, move to the right and into state C. If I find an X, I'll leave it alone and stay in the start state. If I don't find any ones or zeros and only encounter blank squares, they must have all been paired up, so I move to the except state. So at the moment, our scanning head is in the start state. It reads a 0, replaces it with an X, moves one square to the right and into state B. Now the machine has just seen a 0 and needs to find a 1 to pair it with. So state B says, if I see a 0 or an X, I'll leave them alone and move right one square and stay in state B. If I see a 1, I replace it with an X and move to state D. So our scanning head reads a 0, moves one square to the right and stays in state B. Now it reads a 1, replaces it with an X and moves one square to the left and into state D. State D is only entered when a 0-1 pair has been crossed out by X's, so the machine needs to reset for the next count. It says, I keep moving the scanning head to the left, ignoring everything. If I see a 1, I leave it as a 1. If I see a 0, I leave it as a 0. And if I see an X, I leave it as an X. I keep moving until I reach a blank square, which indicates I've reached the beginning of the list of symbols. I then move one square to the right and go back to the start state to repeat the whole process. After another round of this, the machine only encounters X's, so keeps moving right and remains in the start state. When it reaches a blank, it moves into the accept state, and we know that this list of symbols does have an even number of ones and zeros. So that's how one of these machines would work. But here, Turing had another incredible insight. See, at the moment, you would need to build different machines to do different tasks. A machine to calculate square roots would need to be built with a different internal state table than a machine to do addition. But Turing realized that any internal state table could be encoded into a list of ones and zeros. In this way, we could feed the instructions as well as the problem into a new machine, and that machine could perform that set of instructions. Today we know this as a programmable computer. We have computers which we can program to do different things after they've been built. That idea originated right here in Turing's paper. He dreamed up a theoretical machine that could perform the same task as any other of his machines, and that was pretty freaking incredible.
The trading lifestyle doesn't exist. Today, I'm in a place that has a lot of meaning.
Even though this theoretical machine is incredibly simple, it can, in principle, do everything that a human computer can do. This abstract machine, now called a Turing machine, was Turing's definition of an effective procedure. An effective procedure was anything that could be computed by a Turing machine in a finite amount of time. So with that out of the way, he could go on to answer Hilbert's question: did there exist an effective procedure for deciding the truth or falsity of any mathematical statement? Or, as framed by Turing, did there exist a Turing machine for deciding the truth or falsity of any mathematical statement? The way that Turing answered this is beyond the scope of this video. I did make an entire separate video about it called the halting problem, which you can check out after this, but I will tell you that Hilbert's program ended in complete failure, and Turing contributed to it by proving that there was not an effective procedure for deciding whether any mathematical statement was true or false. This alone is an amazing achievement, but Turing's little machines took on a life of their own. By making a definition of computation that was rigorous, people were able to study the nature of computation and its limitations like never before. This birthed the entire field of computer science, which is the study of people of their own. Alone is an amazing achievement, but Turing's little machines took on a life of their own. By making a definition of computation that was rigorous, people were able to study the nature of computation and its limitations like never before. This birthed the entire field of computer science, which is the study of what computers can and can't do, the complexity of algorithms, and the overall nature of computation. Furthermore, by coming up with an intuitive, easy-to-understand model, people were able to turn the abstract and vague notion of computation into a physical machine that could replicate the process. Turing machines are the blueprint of the modern-day computer. Anything from your desktop to your smartphone to the computers on the International Space Station are based on Turing's model. Anything that any of these machines can do can, in principle, be done by a Turing machine. It might just take a bit longer. Now, it's worth noting that other models of computation do exist. Alonzo Church, who would later become Turing's doctoral advisor, actually came up with his own model just weeks before Turing, called the lambda calculus. Turing found out about this just before publishing his own paper, and wrote a quick appendix which showed that Church's lambda calculus and his own model were in fact equivalent, meaning that anything that can be computed by the lambda calculus can also be computed by a Turing machine, and vice versa. However, because of their concreteness, simplicity, and precision, Turing machines were the model that caught on and captivated the imaginations of the mathematics community. Even though they were conceived nearly 90 years ago, there is currently no working model of computation more powerful than Turing's. This is embodied in the Church-Turing thesis, which states that anything that can be computed can, in principle, be done so by a Turing machine. If a Turing machine can't compute it, it's not computable. That's not to say that this might not someday change. There's a growing field of study called hypercomputation, which studies theoretical models of computation more powerful than Turing machines. The trouble is making them physically realizable. Another model of computation that's been getting a lot of hype recently are quantum computers, which, if they work, will definitely bring something new to the table. But so far, Turing's simple model, which he dreamed up at age 22, kind of as a byproduct to answer a totally different question, is still the most widespread model of computation to date. This video was an origin story about one of the most fascinating and relevant fields of study, but there is so much more to computers and algorithm that's worth exploring. If you'd like to get a real handle on the fundamentals of computer science, hearing about it in a video probably isn't enough. But there is good news. You can learn about it the same way I did, through interactive courses on Brilliant. In this Computer Science Fundamentals course, you can learn how to write programs, search for solutions using the computational method of brute force, and
Hello, I'm John Gustafson, and this is Charles Schorb, and this is a replica of the first electronic digital computer, the Atanasoff Berry computer. The Atanasoff Berry computer, or ABC, was built at Iowa State between 1939 and 1942. This replica was completed in 1997. Using this replica, we will take you through a complete example of using the machine to solve a set of equations. Hello, I'm John Gustafson, and this is Charles Schorb, and this is a replica of the first electronic digital computer, the Atanasoff Berry computer. The Atanasoff Berry computer, or ABC, was built at Iowa State between 1939 and
Persil ví, že ne každý by se na práci z domova oblékal, ale ty ano. Persil ví, že ne každý by se na práci z domova oblékal, ale ty ano.
Mukosolvan. Rychlé řešení, jak být opět spolu.
Now it's my pleasure to introduce Dr. John Atanasoff, who is going to tell his story of the invention of the first electronic digital computer. Dr. Atanasoff was an applied mathematician and physicist working in the physics departments at Iowa State, and I think at the time working on analog techniques for solving Laplace's equation and also doing some statistics using punch cards. In about 1936 to 37, at least according to the various writings I find and also in talking with him, that he really abandoned the whole idea of using analog techniques for computation, and by 1938 had worked out the details of memory and logic using an electrostatic drum. Then in 39 he went on to design this machine for solving 30 simultaneous linear equations. He then showed this work to Mauchly in June of 41. In essence, he has embedded the idea of the analog in what he called the impulse digital calculator, at least there. But if I spend any more time introducing him, I will begin to tell his story, and he's going to tell it better than I can anyway. So this is indeed an honor to have with us Dr. Atanasoff. Thank you.
Dr. Bell, ladies and gentlemen, I'm very grateful to Professor and Mrs. Bell, to the museum and to Digital for the opportunity of presenting my early ideas on computing. I'm very grateful that fate should have placed me at the beginning of this great adventure. I had great expectations, but none that matched present achievements and none that could possibly match what we all expect of the future. Computing will have no appreciable negative effect on our energy situation. On the contrary, it will have a large positive effect by sharpening our mental process to affect economy, and I think this is a major matter too. Tomorrow I'm going to visit Digital Equipment Corporation. Thinking of this visit is a poor mental preparation for a lecture on ancient ideas, but here goes. It's part of the title there. I will not burden you with most of my homely efforts to begin life on this planet. I'll however mention a few things in my early life which influenced my later interest in computers, and I want to tell you about my first computer. The year was 1913. My father was an electrical engineer for a phosphate mine, and he wanted a slide rule. It came after several weeks by mail. There wasn't any. We didn't have a car in 1913, and if you'd taken a train and gone anywhere, you probably couldn't have found a slide rule even. This was in the lower part of Florida. He really didn't need the slide rule very badly. And the slide rule was left around the house, and I had access to it. And I read the instruction manual and got to where I could operate it a little bit. However, at the age of 9, I wanted to know why. And here started a program, and I call this a preposterous memory that I have in regard to this enterprise that I had to try to find out about the slide rule. And I started to work on the slide rule and put on 2 or 3 or more hours a day. And eventually, I reached a place where I knew the definition of logarithms, and then my mother was pretty good in algebra. As long as I was staying in the algebraic field, she could help me. Dad wasn't paying much attention. But I commenced moving into calculus. And I got Maclaurin's formula and a series for logarithms. And I calculated logarithms to the base 5. And this took perhaps most of my spare time for 4 months. In 1913, I also studied radio and radio telephony. I wouldn't mention it here, except that the books were published in England. We hadn't reached that stage in the United States. There wasn't much to write about telephony, except arcs. You know, an arc was the only way we knew how at that time to generate continuous waves. But this book also contained my first information on Poulsen's magnetic wire, and this laid the foundation for all of our magnetic recording in the computing art. Now, I don't know what the situation was abroad, but my mother had a large arithmetic which she'd studied in the 8th grade. It contained many other topics than those usually included in what you'd call arithmetic and what I would call arithmetic. But it had a chapter on numbers with other bases than 10. And I studied this with great care, and a good deal of several of the pages I can remember to this very day. My mother said it was Robinson's arithmetic. I'm not quite sure. In 1913 to 15, I had contact with a comptometer and a Monroe. Monroe had a carriage that could be raised I suppose we have some in the museum, and you snap a couple snaps and raise the carriage, and you could look inside and see how it worked, which I immediately did. And this is my memory, sharp and clear, but I wanted to be sure that I wasn't going to tell you something wrong, so I got a hold of Mr. Stan Schultz, your Mr. Stan Schultz, who came to my house to make a pickup. And he was formerly with Monroe, and he said that I asked him when they started making Monroes. I wondered if they really had them in that day. I remembered it very clearly. He said they did. He said they started manufacturing Monroes in 1910. I studied the International Encyclopedia on calculators. It was a very good discourse, but it didn't have any much work on Babbage. Early in high school, I was wondering what I was going to be, and early in high school, I decided on mathematical physics as my life work. I might say it's been good to me, and I would do it again. When I got to the University of Florida, I took electrical engineering because it was the most theoretical course on the campus. But I had machine shop, forge and foundry, and power, but no electronics. You know, at that time we were just building little radios that could hear KDKA. Now, in my first year of graduate work, I found a proof in Hobson's real variables, which employed base 2 numbers. I'll bet I haven't looked at it since that day, since that term, but I'll bet you if you look, you'll find in Hobson's real variables, it's laid away in the library somewhere, you'll find this base 2 number theory there. And it's a simple matter, but in the class of 10 people, I was the only one that had ever heard of base 2 numbers. Even professional mathematicians didn't know it. When I took a PhD thesis, I worked on the polarizability of helium. J.H. Van Vleck was my major professor. He was head of the physics department at Harvard for a number of years, and then afterwards finished up with some kind of a position. He got the Nobel Prize in 1977, and I thought I would ask him to come to this lecture, but he died 2 weeks ago. I used the wave function of Hillhouse in defining helium, and then applied a perturbation, and then calculated the polarizability of helium, and compared it with actual physical measurement of the polarizability of helium. And I think the originally I got 5% accuracy, and later I got 2% accuracy. It took 8 weeks of hard work with Monroe for me to do that thesis, and I got polarized towards computers in this instance. After getting a PhD, I returned to Iowa State College as assistant professor of mathematics, and I knew what I needed to do very quickly. I needed to study electronics, and I started right in and studied Vanderbilt. Do any of you know that book? An old book, but it was good in its day. And then I built a few receivers and got fairly good at it, and that's what I depended on in building a computer later on. I also studied IBM equipment, and Professor A. Brandt helped me. He was in statistics, and we were looking for some project that we could use an IBM tabulator for, and I thought that we could make out in analyzing complex spectra with that. A critical examination of complex spectra, a critical examination of the IBM tabulator showed me that it wouldn't do it, and I commenced to think, and I decided that what I needed to do was take an IBM tabulator and add some additional equipment to it and make it work. We did that, and we published a paper in the Journal of the Optical Society. I have it here, and the last pages of this book, it says something nice about IBM, but some years later, I saw some of the literature that IBM put out at the request of the court, that they divulge every piece of paper they had in their files that contained the name Atanasoff. And one of those papers said, keep Atanasoff out of the IBM tabulator. Well, I didn't have too much competition at Iowa State University, and pretty quick I was made assistant and then associate professor of mathematics and physics. And then I had graduate courses and graduate students. And I got some graduate students that were interested in linear partial differential equations, and I had a student that that worked on the theory of, oh yes, I might tell you, if you're in partial differential equations, you can't make much progress by trying to solve them. You can't solve them in any ordinary sense. But all you can do is to approximate the answer. There are too many functions necessary to solve those equations. They're all over the map, things you've never heard of before and no one else has ever heard of before, and you just can't get at the solution that way. You have to approximate it. And you commence to approximate it. I have a, yes. I have a couple of slides here to indicate how we went about solving the differential equations. I'm afraid I can't use a pointer on it, but in the first slide there, I showed you how you could start with an ordinary expansion with ordinary coefficients, and in two separate stages move it to the equation 3. And in equation 3, we do not define the coefficients in terms of integrals, but in terms of the use of a functional. You see that capital F there? I don't know how well you can see that in the third equation there, and it shows you that you could get the coefficient by the use of a functional instead of by an integral form. You'd think it's just a simplification of the previous results, but it really isn't. It represents a generalization of that. In the next equation down there, I show you how to select the phis and the f's in order to make that expansion correspond to Taylor's expansion. Now that's really just a start on this. And here's a couple of equations that we're going to try to solve to get an approximation of. Now we're going to use a system of functions phi sub I and a system of functionals f sub j. I and j both run from 1 to infinity in theory, but in doing an approximation you'll take a finite number of them. And you can see the two equations given at the top there, and we substitute in place of the unknown u an expansion in terms of the phis, and then we apply the f's, and we come to the last equation down there in either one, and there are slightly different kinds of equations, and I could tell you more about that, but probably. Now those last system of equations there are a system of linear algebraic equations, because everything else is known. And to approximate the solution, you have to solve that linear system, and so we were getting very interested in solving them. Now, in order to solve any particularly hard problem, you'll have to have not we could easily solve. You know, you can sit down with a piece of paper and solve 2 or 3 equations and 2 or 3 unknowns. 8 or 10 equations and 8 or 10 unknowns will make you pretty busy if you don't have a computer. But we needed 20 or 30 equations and 20 or 30 unknowns to solve that problem, and that was a problem that was bugging us. Now, I might say that those equations given there are very like the equations that are known for approximation. They're called Rayleigh-Ritz, Busnay, and perhaps by a modification, the Treff system of approach to the equations. This is what actuated me really more than any other problem to get interested in the computing art. As I felt the basic need for more powerful methods of computing, I commenced to take stock of what methods and apparatus existed. It soon became evident that one could divide all calculators and all computers and computers into two classes, analog and digital. I believe that division was ours. The first word, analog, was of my coining, but I missed the second. I didn't call them digital. Almost put digital out of business, didn't I? I called them computing machines proper. I will use the word digital in everything that follows because it's a better term. In analog machines, the numbers are represented directly by some physical quantity. The larger the number, the larger the quantity. The quantity can be movement, velocity, or voltage, or in fact any easily measured physical quantity. In a digital computer, we must use some physical quantity to represent the number. We do. We use some quantity there to represent the number. But the physical quantity is related to the number by what I call the Hindu-Arabic number system. Although the base of the number system need not be 10, but can be any integer above 1. Now, I list some analog computers here, the slide rule, and then I was thinking about building a slide rule using 35 millimeter film for the slides, putting it over sprockets. I don't think anybody else ever built one, and I didn't build one either. It turned out that but with reasonable lengths of moving picture film, I could work to 1 part in 100,000. This is a way you'd make a slide rule do better. This is what you have to do. If you take any analog process and try to make it more accurate, then at that time the publications were filled up with the Bush differential analyzer. Professor Vannevar Bush was at MIT. You ought to know something about him. Very fine analog computer, but I didn't get interested in it too much. I couldn't really believe that it was a project for the future. Now I might tell you of one or two other analog computers. You take the anti-aircraft fire director for military purposes. It has in it an analog computer. Now, I don't know whether anybody's ever built a digital computer into that. Then there was a device that was used in those days that was called a Fourier analyzer, and it used motion as the quantity. And then later on, Mauchly told me he was going to build a Fourier analyzer. I guess he built one, which used electrical device. And then we had we built in my laboratory. We built an analog computer for solving Laplace's equations and 2 unknowns. And here's I don't have a picture of the machine. It's rather simple. And here's a paper that we published on that. Now, when it came to digital computing, we had the miscellaneous simple computers, Comptometer, Monroe, and Marchant, and then we had the only 2 bigger machines that we had were the IBM and the Remington Rand tabulators, and those both existed in that day, say about 1936. This is the analysis that I gave. I soon found out that no machine or system available could solve the growing list of problems of theoretical physics, technology, statistics, or business. Analog methods were generally specific for some special problem. That's the trouble with could solve the growing analysis that I gave. I soon found out that no machine or system available could solve the growing list of problems of theoretical physics, technology, statistics, or business. Analog methods were generally specific for some special problem. That's the trouble with the Bush analyzer as far as that goes. And to adopt them would take time. You have to reorganize them to start them on a new job. They are also of low accuracy, perhaps giving three or so significant figures. So I turned my attention to digital methods. These could be of sufficient accuracy, but operational flexibility was limited. Even the largest IBM tabulator of the day had an internal memory of, the largest one in existence had an internal memory of 266 bits. To use such methods would require a very new art. I didn't want to do computers. I had graduate students doing other things, and I didn't want to build them. But somewhat sadly, I moved in that direction. There I was in 1936, turning my mind to invent a new digital computer, not knowing how it would be built or how it would work. However, I believed that it should be fast, accurate, and flexible. I wrote out a few ideas. You will recognize an item or two from my early years. Of what stuff would my digits be constructed? See, we're going to use some quantity to represent digits, and what stuff would that be? And would it be mechanical, electrical, or some other? And what would the structure be? And the only thing I could think of was to separate memory and computing. And maybe it wasn't a bad idea. And now I thought, does base play a role? If we're building a digital computer, what are we going to do about the base? And what determines this? How should I do computing? What was the computer going to be like? And how should memory be constructed? I had all these words at that time, and for base 2 numbers, I thought of a two-step mechanical system, ferromagnetic material, going back to the wire, you know. And I thought that was an awful good idea. In the end, I didn't use it. A two-state vacuum tube circuit, and a capacity with 2 states of charge. That's what I did use. And then if you wanted to build bases bases of size n, well, you could use a ring or circle of metal with n stops. That was common in the base 10 computers throughout the older days. A combination of base 2 elements to yield a base n, and a vacuum tube ring circuit. You should realize that these concepts represented a hodgepodge of ideas. I tried again and again to sort them out. Nothing seemed to work. After months of work and study, I went to the office again one evening, but it looked as if nothing would happen. I was extremely distraught. And then I did something that I did in those days, but I've had to stop lately. I got in my automobile and started to drive. I drove hard, so I would have to give my attention to driving, and I wouldn't have to worry about my problems. And whenever and once in a while I would commence to think about my efforts to build a computer, and I didn't want to do that, so I'd drive harder so I wouldn't. Here, I drove towards the east. I was driving a Ford V8 and with a south wind heater. I don't suppose you know what a south wind heater is. Pretty warm, but the night was very cold. It was in the middle of the winter, in 1937 and 38. When I finally came to Earth, I was crossing the Mississippi River, 189 miles from my desk. You couldn't get a drink in Iowa in those days, but I was crossing into Illinois. I looked ahead and there was a light. Of course, it was it. And I stopped and got out and went in and hung up my coat. I remember that coat. And sat down at the desk and got a drink. And then I noticed that my mind was very clear and sharp. And I knew what I wanted to think about, and I went right to work on it and worked for 3 hours, and then got in my car and drove slowly back to Ames. And I got in my car. I knew what I wanted to think about, and I went right to work on it and worked for 3 hours, and then got in my car and drove slowly back to Ames. And I had made 4 decisions in that evening in the Illinois Roadhouse, used electricity and electronics. That meant, of course, vacuum tubes in those days. Used base 2 in spite of custom for economy. Used condensers but regenerate to avoid lapses. Compute by direct action, not by enumeration. You know, it's an easy thing if you know about number systems to just have things that count, a kind of an internal counter that gives you enumeration, but I was going to do it by direct action. This concept was new. I had yet to devise the circuit. I didn't know how I was going to do it, but I thought I could do it. After the trip to Illinois, I took time to go over the decisions, and in the end I decided to build according to decisions made in a short time in another state. I had a few points I want to make with you. In vacuum tubes, for a period I would think that vacuum tubes would not be stable enough for the purpose. And then I would remind myself that I was not building an analog but a digital device. I'll go over some parameter in a mechanical calculator, and then I knew that such parameters do not have to be very precise to give not just ordinary results, but perfect results. That's a characteristic of a digital machine. You all know that. So vacuum tubes were in as a component of a computer. I might say that immediately I was faced with the cost of vacuum tubes, almost immediately, because they were large, they used quite a lot of power, they're large in initial cost. I thought I wanted a vacuum tube with the, I used to say the size of a grain of wheat. I thought I wanted a vacuum tube with the size of a grain of wheat. And I thought I knew how to do it. I'll tell you how. And this was in my mind, but I never did it. You know, we used to use galena and silicon carbide to rectify the current in a radio. And galena would be used without DC bias, but when we use silicon carbide, well, we'd apply an external voltage. And here's the thing. Did you know some of those silicon carbides would oscillate? And I don't suppose did anybody in the room ever hear of silicon carbide oscillating? Anybody hold your hand up? Not many people knew it at that time. But I knew that if it oscillated, that it was amplifying, and hence all I needed to do was to strip it off and straighten it out, and I could get an amplifier that way. Now, in the Roadhouse, I thought that I could build a computing circuit with a vacuum tube circuit that would receive the two digits being added or subtracted in a given level, given numerical digit there, and would receive the carryover into that place and would give out the addition or the subtraction which went into that place, and also give out in another point the carryover. Although I knew something, I'd already studied something about Boolean algebra at that time, but I didn't design this by Boolean algebra. I noticed other people design such circuits by Boolean algebra today, but I designed it by sheer awkward force. I just went to work and did it. In my notes, I have one page that notes that this process deserves more algebraic finesse. It should be noted that here's another point. It should be noted that one digit is calculated in full, including carryover, before the next place is calculated. We call this serial calculation. Now, I expect you call serial calculation something else, but that's what we call serial calculation. And this decision represented a major advance in computing. Babbage did not have it. I think that each of you don't use anything else. As far as I know, now you must tell me if I'm wrong. I saw Harold Anderson on the campus, and I said to Harold Anderson, I need a man, and he says, I have the very man for you, and it was Clifford Berry, and I couldn't have had a better man, and he was absolutely tops in all respects. And In the fall, he and I went to work on the job, and by Christmas, we had a prototype in operation. And I think I can show you the prototype. There it is. Now, this prototype was designed to work out all the aspects which worried us about this kind of a competition. Now you see up at the left-hand side up there, we have some discs, and on those discs where are the condensers, which are going to be the memory. And we needed a name for those discs, and I use the Chinese abacus. I call those discs abasci. And that disc, I had two sets of condensers. The one on this side, we call the keyboard abacus. Consists of a row of condensers around there. I believe there are 25 in that particular machine. And that'll give us 25 base 2 places there. And on the other side, there is another row of discs, another row of condensers, and it's called the computing abacus. Keyboard abacus and the computing abacus. And the keyboard abacus came from the point that if you use that you get that more or less takes the place of a keyboard in a computing machine. Now down at the left here, we have 3 sets of chassis at the bottom. For the first chassis there is the circuit that regenerated the keyboard abacus. The second one is the add-subtract mechanism, which I devised. You're going to hear more about that later. And the add-subtract mechanism also regenerates the computing abacus. And the other chassis there is a power supply. There are a couple of additional points in there that you ought to know something about. We have to, in order to get the voltages to work out right, we have to boost the flip ring at the inner edge of the condensers. It's called boost. You'll see boost there in some places. I can't see it very well from where I am. And then there's another rotating condenser, commutator with a condenser on it, which is a carryover capacitor. And that picks up the, when the machine is working at one level, it picks up the carryover.
I will try to complete this one later, not now. But it's interesting things. Computer History Museum. Subscribe to this one. Okay, it seems to be a nice channel, so by the way, I use 2 Chromes, like this one, which is the 606 for chaos work. This is one for documenting the things. Like if I found something really useful, I can utilize it in somehow. I move it to this one, and this is one like mostly I will junk things. Nonetheless, I think there are a GPT for summarizing. Let's